Okay. Okay.
Hearty welcome to National Virtual Conference on Emerging Trends in Applied Mathematics. Welcome to day 2. Today we are having an invited talk by Dr. Paul Isaac sir. Here I am to introduce Paul Isaac sir by our dear beloved colleague Dr. Sister Alfonsa Matthew, our vice principal, and also our NAC peer member team, and also IQAC member of the core team. Here we are to introduce Dr. Paul Isaac sir by Dr. Sister Alfonsa Matthew. Over to you, sister.
Okay, thank you. A very good afternoon to another present here. Today we are in the second day of our national webinar on emerging trends in applied mathematics. The resource person for the day is Dr. Paul Isaac, Associate Professor, Bharatmata College, Trikakara. Dr. Paul Isaac has long 28 years of teaching experience and he has been involved in research for many years. Dr. Paul Isaac has published more than 50 papers in national and international journals, and he has completed 3 minor research projects. He is a vibrant research guide at the Research Center, Bharatmata College, Trikakara. 4 PhD has been awarded under his efficient guidance, and many are pursuing under his supervision. His area of expertise is fuzzy mathematics and differential geometry. He is a member of several board of studies of various autonomous colleges, and also Dr. Paul Isaac is the General Secretary of Kerala Mathematical Association. St. Thomas College is fortunate to have such an erudite mathematician to be the resource person for the day of this national webinar by Department of Mathematics, St. Thomas College. On behalf of the management, principal, the Department of Mathematics, and all the participants, I accord to you a warm welcome, sir. Over to you, sir. Thank you.
Thank you very much, Sister Alfonsa and Sister Julie, for your nice words about me. First of all, I thank the management, principal, head of the Department of Mathematics, and the convener, Sister Julie, and other faculty members for giving me a chance to deliver a talk on fuzzy sets. It is a privilege for me to give this talk in a college more than a century old, St. Thomas College, Trishur. So I thank once. In this talk, my aim is to give the basics, the fundamentals of fuzzy set theory. You may be knowing that fuzzy set theory as a branch of mathematics began in late 1960s or 1965. Lord F. Sade in 1965 introduced the concept of fuzzy sets. And with respect to the fuzzy sets, the ordinary sets are known as the classical sets or the crisp sets. So the transition from the crisp set theory to fuzzy set theory is a century old, many centuries old history. In fact, there were three traditional laws of thought from the period of Plato itself. First law is the law of identity. That is, for any proposition, A is equal to itself, or whatever is. And the second one was the law of non-contradiction. And sometimes it is also called the law of contradiction. That is, a proposition cannot be true and false, true and not true at the same time. That is, nothing can both be and not be. And the third law is the law of excluded middle, or the excluded third. That is, everything must either be or not be. That means everything must be either true or false, nothing in between. Or everything must be yes or no, nothing in between. Or in digital language, everything must be 1 or 0, nothing in between. That is either A or not A. And the history of these three traditional laws, as I told you, begins from the period of Plato, and it proceeds through Aristotle. Even the principle of contradiction and excluded middle, that is the second and third law, can be traced back to the period of Plato. Now we consider the various logics, classical logics, or the crisp logic, or the Boolean logic, whatever it is called. The other one is the so-called inductionistic logic, under which fuzzy logic comes. Fuzzy logic, inductionistic fuzzy logic, interval valued fuzzy logic, all this comes under inductionistic logic. In classical logic, there are two possibilities: A is true or A is false. If A is false, then that means that A is true. That is two cases, A and not A, or negation A. And negation of negation A means A. But in inductionistic logic, we can say that this statements becomes A is provable, A is disprovable, and if A is disprovable, that is the place of negation A. But here it doesn't mean that A is provable. A is disprovable. It doesn't mean that A is provable. That is the difference between classical logic and inductionistic logic. In classical logic, negation of negation A is A, but in inductionistic logic, that cannot be true. And the law of the excluded middle. Already, as I mentioned, negation of negation A is A. There is nothing in between A and not A and negation A. That means if A is not false, then it must be true. A is true. But in inductionistic logic, this is no longer true. That is, the law of excluded middle is not always true. That is what the essence of the so-called Gödel's theorem. Now, you might have heard about this term, reductio ad absurdum. That is the method we use to prove several theorems in analysis or mathematical, to prove several mathematical concepts. Suppose we have to prove the statement P implies Q. Suppose we have to prove this statement P implies Q. For what? For this purpose, we assume negation of Q and we prove that negation of Q implies negation of P. That we assume the contrary. We assume P, and we assume, if possible, we assume that Q is not true. And from this assumption, we arrive at a contradiction, so that we get negation of Q implies negation of P. And from that, we conclude that our assumption is wrong, so we conclude that P implies Q. That is a method of proving several results or several theorems in analysis or abstract algebra, many branches of mathematics. And this method of proving is known as reductio ad absurdum. That is, proving a statement A, we assume its contrary, that is negation of A. And after some arguments, we arrive at the conclusion that negation of A is not possible. So we conclude that negation of negation A holds. Negation of negation A means it is A under crisp logic. That means yes, we conclude that A is true. But in inductionistic logic, the third step, negation of negation A is A, is no longer valid. But in crisp logic, we conclude that negation of negation A means A. Heraclitus is the man, is a man before Socrates, a Greek philosopher, proposed that things could be simultaneously true and not true. Plato, again we know that he is a Greek philosopher before Christ, laid the foundation or what is now known as fuzzy logic. So though Sade introduced fuzzy set theory in 1965, the history begins from the period of Plato. And he pursued that there is a third region beyond T and F. T and F means truth and false. There is a third region between truth and false. And Lukasiewicz, a Polish philosopher, in 1920, after several centuries, described a three-valued logic, and he described the third value as possible, and he assigned a numerical value between the values assigned to true and F, true and false.
Hello, sir. Excuse me, sir. Hello, sir. You are not audible, sir. Hello, sir. Hello, sir. Can you please speak?
Hello, Ekavo. Hello, am I audible? Hello, hello.
Yes, sir, you are audible now. Please
I don't know.
continue, sir.
I don't know what happened.
Okay, sir. Continue. Please continue, sir. Thank you.
Heraclitus is the man who proposed there could be something in between true and not true. Plato is the man who proposed that there is a third region between true and false. Lukasiewicz in 1920 described a three-valued logic, and he assigned a numerical value between the values of P and F. Ronald Booth, an American computer scientist and mathematician, also proposed a three-valued logic similar to Lukasiewicz. And Ronald Booth, you may be familiar with this name. He is the man who introduced the LaTeX. Usually, people who do scientific research or scientific publications type in LaTeX. So Ronald Booth is the man who introduced LaTeX. The man Lukasiewicz and Ronald Booth. And in India, this fuzzy set theory introduced by 4 or 5 people in 1970s. One among them is Dr. Professor Trivikraman from Cochin University of Science and Technology. All present generation students or teachers may not know him, but he is very familiar to the mathematical community in Kerala and India. His name is very familiar. So, as I told you in CRISP logic, only two values, either true or false, or either yes or no, or either 0 or 1. But in fuzzy logic, there are in between values. Between 0 and 1, we give values between 0 and 1. So this is the concept of fuzzy logic compared to the logic of classical sets or classical logic. So in set theoretic language, classical sets are called CRISP sets. In set theoretic language, an element, there will always be a universal set. So from an element X from that universal set belongs to A or not belongs to. Only these two possibilities are there. Only these two possibilities are either an element belongs to a set A or not belongs to a set, not belongs to the set. So we can characterize this set by its characteristic function. Characteristic function, we define it as chi A of x is equal to 0 if x does not belong to A, and equal to 1 if x belongs to A. Only two values are possible. If it is a member of A, we give the value 1. If it is not a member of A, we give the value 0. But when we come to, this is some pictorial representation of CRISP set or classical set. We consider the set of people as the universal set, and we consider young people, the set of young people as a subset of it. Why? Then we are defining those who are of age less than or equal to 25 belong to the set N. So up to the age 25, we include those people in the set N. But what about 25 years and 1 month or 1 week age? According to this definition, he is not included in this set. But we know that the real sense, 25 years and a week is not at all true to say that he is not a. So we define the fuzzy set. In fuzzy set, again we assign a membership value for each element. And this value may take between 0 and 1, any value between 0 and 1, including 0 and 1. In crisp set, only two values are possible, either 0 or 1. Either 0 or 1. Only two values. But in fuzzy sets, we give values, any value between 0 and 1. And again, we can consider the set N as a fuzzy set. So we give membership value 1 up to the age of 25. Here we can see that we are given the value here up to the age of 25, the value 1 is given. And from 25 to 40, when we move around 25 to 40, we give values. Here it is given as linearly, so that when it reaches the age 40, his membership value is 0. And if A is of age 30, his membership value will be, say, 1 by 2. And at the age of 25, the membership value will be 1. So from 25 to 40, we give membership values 1 to 0 in a decreasing manner. And from 40 and 40 above, we give the value 0. And we do not say that he is young if that person is of age 40 or more. And this is the man Lotfier Sadeh. He died recently, 3 years back in 2017. He is an Iranian origin. He is of Iranian origin, but he was a scientist, engineer, professor at the University of California. He was the man who introduced the fuzzy set in 1965. And Professor Trivikraman, just before introducing to the present generation, former head of the Department of Cochin University, Professor Trivikraman, he was the person among 4, I think, or 5, who introduced fuzzy sets in India. He introduced fuzzy sets in Kerala. He is the only man who introduced fuzzy sets in Kerala in 1970s. So the notation of fuzzy sets, and we denote a fuzzy set A as, we write it as a pair. The first one is the element, and the second one is the membership value. And X is the element of the universal set. X is an element of the universal set. And the membership function takes the values from 0 to 1. Can be assigned any value between 0 and 1, including 0 and 1. So see that in classical sets, only two values are taken, 0 and 1. Set to 0 and 1. But in fuzzy sets, including 0 and 1, any value between 0 and 1 can be taken. So the classical set becomes a subset of the fuzzy set, because if this fuzzy set mu A takes only the values 0 and 1, nothing in between, then it becomes a crisp set, classical set. So the classical set is a subset. Classical logic is a subset of the fuzzy logic. So classical set is the particular case of the fuzzy logic, or the fuzzy logic can be considered as the realization of the crisp logic. Some examples are given. It is simple examples. We consider a universe consisting of only 8 elements, can be considered as the courses a student may take in a semester. And here the fuzzy set A is defined as 1 with the membership value 0.1, 2 with membership value 0.3, the course 3 with the membership value 0.8, 4 with the membership value 1, and so on. That means that course 1 is taken by only 0.1 membership value with a point. That means that if there are 100 students, only 10% of the students takes the course 1. There are 30 students, there are 100 students, only 30 students takes the course 2. 80 students takes the course 3, and only all students, all of them takes the course 4, and so on. So we give a grade to each member of the set U.
This is an example of a fuzzy set. And the same thing can be represented. Alternatively, we can give the representation as A 0.1 bar 1 plus 0.3 bar 2 plus 0.8 bar 3. And please see that this is only notation. Don't think this was the addition of some fractions. So it means that 0.1 is the membership of value of 1, 0.3 is the membership value of 2, and 0.8 is the membership value of 3, etc. It is not the addition of fractions, it is only notation. And if we are considering a continuous universe instead of a discrete universe, if we are considering a continuous universe, for example, suppose we define about 50 years old, we can define the membership value as mu. If take the set as b, mu b of x is equal to 1 divided by 1 plus x minus 50 divided by 5 to the power 4. Something like that. There are several ways of defining the membership value, and here it is defined like this. And we can see that the graph, the pictorial representation is given here. If x is of age 50, then we get the membership value as 1 divided by 1 plus 0. So it is of value 1. Membership value is 1. Well, if x is 49 or 51, we'll get the same value for the age 49 and 51, and so on. So it is a graph which is symmetric about this line, vertical line. Not drawing. It is symmetric about the vertical line, the vertical axis. And also the same fuzzy sets can be represented. This is also another notation. We are, instead of writing using plus signs, we may write sigma mu a xi by xi if the universe is discrete. If the universe is continuous, we may write it as integral. It's only a matter of notation. And this bar slash, do not take it as division. It's only a demarcation from the membership value to the element. So another example we can consider, the membership values we give depends on the context. For example, suppose we consider the concept tall. In Asia or in India, if a man is of height 5 feet and 10 inches, we say that he is tall. Almost nearly, we give the value membership value almost near to 1. We say that he is tall. But in USA, 5 feet 10 inches, they will give only value 1 by 2 because people in USA are taller than people in Asia. But when again we come to NBA, NBA means National Basketball Association. So we know that basketball players are very tall. So for basketball players, 5 feet 10 inches. I don't say that 5 feet 10 inches is tall. So the membership value is given nearly equal to 0. So these are the concept of fuzzy set. So it may vary depending upon the context. So another concept, young, middle-aged, and old. Up to say at the age of 25 or 22, 23, we give the full membership value for young, the concept young. From there, the membership value decreases, becomes 0, and he reaches the age of 45. And after that, the set young has membership value 0. But the violet line, if we consider middle-aged, we give the membership value 0 up to the age of 20 and gradually increases for the set middle-aged. And from say 35 to 55, from 35 to 55, we gave membership value almost equal to 1. And from 55, the membership value decreases and becomes 0 when we consider the set middle-aged. Similarly, odd up to 45, we do not say that a man is odd. So we give value, membership value 0. Then gradually membership value increases, and when he becomes 65, it almost reaches 1, and after that the membership value is 1 when we consider the fuzzy set. So these are some examples to understand the concept of fuzzy sets. So a fuzzy set is actually a generalized set. A fuzzy set is actually a generalization of the classical set. And this is the statement made by Kaufman. And the logic is many-valued or multi-valued or multivalent. Boolean logic or the classical logic, that is the 0-1 logic, is a subset of fuzzy logic. And in fuzzy logic, everything is a matter of degree. And here are some terminologies connected with the fuzzy sets. Suppose we consider the elements x in the universe such that the fuzzy value mu of x is equal to 1. The highest possible value is 1. So this set is known as the core. Core is a set of all elements with the membership value exactly equal to 1. The set of all elements with the membership value mu of x greater than or equal to 0.5. It is known as width of the fuzzy set. And if we consider the elements with the membership value greater than or equal to a given alpha, it is called alpha cut. It is given here. So core is set of elements with the membership value 1. Width is set of elements with the membership value greater than or equal to 0.5. For a given alpha, set of elements with a membership value greater than or equal to alpha is called alpha cut. And the set of elements with the mu x strictly greater than 0, positive, this is called the support. This is called the support. So these are some terminologies associated with the fuzzy sets. Again, some more terminologies. The highest membership grade is known as the height of that fuzzy set. If the core is non-empty, then that fuzzy set is called a normal fuzzy set. Core means number of the elements in the set with the membership value 1. If at least one element is there with the highest possible membership value 1, then we say that that set is a normal fuzzy set. And if there is only one element with the positive membership value and all other members are having membership value 0, then such a fuzzy set is called a fuzzy singleton. The other two definitions are associated with the fuzzy numbers. I am not giving it now because particular case of fuzzy subsets of real numbers. Again, as we define convex functions, here also the fuzzy set is said to be convex if the corresponding function mu a is convex. That means that for lambda in 0, 1, mu of that means if we draw the graph, if it is go like this, it is convex. If it go like this, then it is not convex. So here, if two sets are convex, two different sets, two convex fuzzy sets, but here it is not convex. And as in the case of classical sets, we have the set theoretic operations here also. In the case of fuzzy sets, we said that a fuzzy set A is a subset of B if the corresponding membership values mu A of x is less than or equal to mu B of x for every element in the universe. The complement is defined as, that is, we define the membership value in the complement fuzzy set as 1 minus the membership value in the fuzzy set A. This mu A bar of x is equal to 1 minus mu AX. And the union is defined as we have two fuzzy sets A and B. And for an element X, we define its membership value as we take the membership value in A and the membership value in B, and we take the highest one. The set thus obtained is called the union. That is mu CX. The membership value in C is said to be A union B if the membership value in C is the maximum of membership value in X and membership value of X in A and B. That is join of mu AX and mu BX. That is the maximum of the supremum of mu AX and mu BX. Now we define intersection as the minimum. These are the pictorial representation of here the graph of A is completely below the graph of B. So here this is A is subset of B. Here this is A is subset B because graph of A, yellow colored graph is completely below the. Here A is the yellow colored curve, B is this curve, A union B becomes maximum. So we take the upper part only. A union B becomes the upper part like this, shown below here. From this two sets, fuzzy sets, A union B means the upper portions. Similarly, A intersection B means lower portions, like this. This is A intersection B. And A union B is this upper portions. And yes, the complement is 1 minus A. So the complement is obtained as here it is 0, so here it is 1. Here it is 1, so here it is 0. It's like this, just reversing the values. Of course, a complement of A is A. Commutativity is true. A union B is same as B union A. A intersection B is same as B intersection A. Associativity is true. Distributive property is also true. That is A intersection B union C is A intersection B union A intersection C. All idempotence is true. A union A is A intersection A is A. Absorption law is also true. But what is not true? Or what are not true? These laws. De Morgan's laws. Sorry, the complementation. Sorry. What is not true is this one, this two. De Morgan's law is also true. A union B bar is that is A union B complement is A complement intersection B complement. A intersection B complement is A complement union B complement. What is not true is of prediction. That is, in classical set theory, A intersection A complement is fine, empty set. Here it is minimum of A and A complement. That need not be 0. So here, in the case of fuzzy sets, A intersection A complement, this is not true. Similarly, the law of exploded middle. It is A union A complement equal to U. That also need not be true in the case of fuzzy sets. There are other definitions of theoretic operations, other definitions for union and intersection. Another definition is given mu of A union Bx, the intersection. Before we define it as the maximum of mu Ax and the mu Bx. The earlier definition we define the union as maximum of mu Ax and mu Bx. Here we define as minimum of 1 and mu Ax plus mu Bx. Sum of mu Ax plus mu Bx may go beyond 1. So we have to take the minimum of 1 and mu ax plus mu bx. Similarly, intersection is defined as, because mu ax and mu bx are between 0 and 1, their product will also lie between 0 and 1. So mu a intersection bx is defined as another way of defining intersection. This is another one for union and intersection. Mu of a union b of x is equal to mu ax plus mu bx minus mu ax into mu bx. Intersection is as in the previous case. So all these concepts can be generalized as T norm and T conorm. T norm is mapping from a product 0, 1, interval 0, 1 cross 0, 1 to 0, 1 is triangular norm. Satisfies this symmetry property, that is T of xy equal to T of yx. We denote T of xy as x dot y equal to y dot x. If we denote T of xy as means that this means that x dot y equal to y dot x. Here it means that x dot y dot z equal to x dot y dot z, that is associative. Similarly, monotonicity, if x1 is less than or equal to x2 and y1 is less than or equal to y2, then x1 dot y1 will be less than or equal to x2 dot y2. And also here the order condition, take the minimum. This minimum of x and 1 is always x. Is considered as minimum. So it is the generalization of, if these four properties are satisfied, this is called a triangular norm. And the conorm is the same way, symmetry is there. The conorm or S norm, sometimes it is called also S norm. Associativity is there, monotonicity is there, but the border condition becomes maximum of x and 0. Just to think it as maximum, s of x0 equal to, these are the generalization of the definition of union and intersection we defined earlier, T norm and T conorm. Examples, maximum and minimum. T minimum, we take T of AB as minimum of AB. It will satisfy all the properties of the T norm. So it is a T norm minimum. Similarly, if we take the maximum or join, it will satisfy all the property of an S norm or T conorm. Similarly, the other two, land and law. Lukashevich and Lukashevich's land and law operator. T of AB is maximum of A plus B minus 1, 0. These are examples of T norm and S norm. There are several ways of defining membership value for an element. The main problem in fuzzy logic is that how we define the membership grade of each element. Earlier we defined at the age of 25, young. After that, gradually decline to 40, gradually decline, and when he reaches 40, the membership value becomes 0, and so on. So the concept of age, how we define the membership value. The concept of tall, how we define the membership value. There are several ways of defining the membership value for an element in the case of fuzzy sets. These are the so-called triangular membership function. This name is because of its shape. Trapezoidal membership function and Gaussian membership function. The last one is the generalized Bell membership. Diagrammatically, we can see that the triangular membership function has the shape of a triangle, and a trapezoidal membership function has shape of trapezium. And the third one is Gaussian membership function. Gaussian membership function has symmetric nature like this, and the generalized function membership function has the shape of a bell. So it is also called a Bell membership function. And see that there are some parameters in the definition. In the triangular membership function, there are three constants: A, B, C. You can see that A, B, C. These three parameters will determine the shape of a triangle. Here also, in trapezoidal membership function also, there are three constants. There are four constants: A, B, C, D. That four constants will determine the shape of the trapezium. And again, Gaussian membership function is defined as the exponential function with the parameter ABC. Definition C, mainly C. So the Bell membership function also there is a parameter C and B. Depending upon the parameters, we will have the several types. This changing A Bell membership function. ABC, the definition here is something wrong. Here divided by A x minus C. The Bell membership function, the denominator is 1 plus x minus C by A. Is written correctly. Yeah. There are three parameters ABC, the Bell membership function. So if we change A, what happens is that the shape of the bell changes like this. And if we change B, the shape of the bell changes like in the second figure. And if we change C, shape is not changed, but some translation occurs there. And if A and B are both changed, what types of changes occur in the shape of the bell? These are the extension principle. That is, just like we define the image of a set under a function. In the case of crisp set theory, we can define the image of a fuzzy set under a function, or a crisp function. Similarly, we can define the inverse image also. So this is the pictorial representation of a fuzzy set. Here the fuzzy set is given, A is given like this, triangular membership function, and its image comes like this. So in fact, B of Y is defined as supremum of A of X if X belongs to F inverse Y. If this is non-empty, supremum. Otherwise, it is defined as 0 if F inverse Y is empty. This is the definition of the image of a fuzzy set A under a function F. Because the time is almost 3 minutes or hour, so I don't want to go in detail with this. For example, though the fuzzy set theory started with the membership set as the interval, closed interval 0, 1, later on, Sarday's student generalized this fuzzy set, taking a lattice as a membership set. instead of interval 0, 1, a lattice is taken as a membership set. And with a lattice as the membership set, we call the fuzzy set an L set or L fuzzy set. J.A. Georgen is the man who introduced the fuzzy set with the lattice as a membership set. He is Sade student. Just after 2 years after Sade introduced this fuzzy sets. The man Georgen, Joseph Amedi Georgen, again University of California. Another type of fuzzy set is inductionistic fuzzy set. In that case, we define a membership function together with a non-membership function. There are two. It is introduced by Atanasoff in 1986. So membership one is there, also a non-membership one is there. That is the concept of inductionistic fuzzy set. So an inductionistic fuzzy set can be written as A equal to element X, its membership value mu A, and its non-membership value mu A, and both this mu A and mu A are functions from X to interval 0, 1. I means interval X to I means is the post interval 0, 1. And the only condition is that here the membership value and non-membership value should not exceed 1. When it becomes equal to 1, if the membership value, sum of the membership value and non-membership value is equal to 1, it becomes a fuzzy set. So, an inductionistic fuzzy set is a generalization of ordinary Faraday's fuzzy set. Again, there are another type of fuzzy set known as interval valued fuzzy set. In interval valued fuzzy set, we give, instead of giving a value as the membership grade, we give the membership grade as an interval. That is, we give the image as interval AB or pair AB, where A is less than or equal to B. Both A and B are elements in 0, 1 with A less than or equal to 1. So if we give the membership grade as a range from A to B, if we give the membership grade as a range from A to B, then we call it an interval valued fuzzy set. I skip all these things. These are the extensions of fuzzy set. Usual fuzzy set is called a type 1 fuzzy set. Another level is type 2 fuzzy sets. This interval valued fuzzy sets, inductionistic fuzzy sets, so-called wave set, layer set. All these are type 2 fuzzy sets. And interval valued inductionistic fuzzy set is again generalization of interval valued inductionistic fuzzy set, or a combination of inductionistic and interval valued fuzzy set. Again, another hybrid generalization. And as an application, fuzzy set theory, the first type of application is fuzzy set theory is applied in almost all branches of mathematics. In fact, my area is fuzzy algebra, in particular fuzzy modules, fuzzy G modules, etc. So, in every branch of mathematics, fuzzy set theory is applied. Algebra, graph theory, topology, and so on, every branch. And the second type of application is used as a modeling language to model real situations. When we consider the concept of young, we cannot say that a person is young if he is of age strictly less than or equal to 25. 25 and 1 month, 25 and 1 week, still young. So, to model such situations, instead of using crisp set theory, we use this fuzzy logic and fuzzy set theory. So it is a very powerful modeling language which can cope up with the large fraction of uncertainties of real life situations. And there are several branches. Sade student Chang introduced fuzzy topological spaces. And first paper in algebra was published by Rosenfeld in 1971. He is this man who introduced algebra in fuzzy group, who defined fuzzy group in 1971. And also as a practical application, now we can see that many household appliances are built using fuzzy logic. So we can find fuzzy logic in shower heads, rice cookers, vacuum cleaners, all several equipments are available which works on fuzzy logic. Washing machine, fuzzy logic controlled washing machines. So in that case, it will decide what degree of laundry, the degree of dirtiness in the laundry, how much soap should it take, how much water to take, how fast and in which direction to spin. All these things will decide depending upon the laundry. And so fuzzy logic controlled washing machines are there. Several also medical diagnostic scanning. Several scanning equipments works on this fuzzy logic. And in fact, in radiation therapy for cancer, this fuzzy logic is applied to locate the tissue which is affected by cancer. This fuzzy logic is applied. So in several ways, in several situations, this fuzzy logic is applied. Handicaps, there are many. I don't want to list all these things. And in traffic light signal also, fuzzy logic is applied to determine the density of traffic in each direction and to give the signals depending upon the density. In all this, there are several ways of real life situations where the fuzzy logic is applied. And main references for fuzzy set theory is Modichon and Malik, Birkhoff and lattice theory. Modichon and Malik is fuzzy commutative algebra, and the main book for fuzzy logic is Zimmermann, fuzzy set theory and its application. And also, there is one book, Clare and Folger, fuzzy sets and uncertainty, and Birkhoff and lattice theory for lattice related theories. And also there is another one book, Fuzzy Set Theory, Introduction to Fuzzy Set Theory by Dubois and Pradey. So there are several standard books available for fuzzy set theory. I think it is almost 3 o'clock now. I think I have to stop here now because we have 12 papers to be presented. So I wish to stop here. And I thank all participants for your patient hearing. And also, I wish all success for this national webinar on emerging trends in mathematics. So I wish all success. Once again, I thank you all, and I stop here. Thank you all. Thank you. Thank you. I think I am audible. No.
Hello.
No.
Thank you, sir. Here I am to thank Dr. Paul Isaac, sir, for his valuable presentations regarding fuzzy sets. Fuzzy sets is a new concept in applied mathematics, which is unknown to many of the other streams, in which a thing could be in a way true and false together. So I hope the students are having some idea regarding fuzzy set theory, which is intrinsically connected to mathematics. Actually, whenever we say about numbers, usually we mathematical people, we say that it is 1, 2, exactly like that things. But there are concepts in which we can consider in mathematics also like that. So, on behalf of the organizing committee and the Department of Mathematics, our dear HOD, Dr. Saju M.I. sir, and all the faculty members and all Santom family, I would like to extend our immense gratitude to Dr. Paul Isaac sir. Dear sir, thank you for your enriching sessions and also for the paper presentation sessions, which we are to. So here we are winding up the session officially. And so within 10 minutes to 15 minutes, we will start the next session of PowerPoint presentations. So we continue to be in this live streaming for 10 minutes more. And after that, you can fill up your feedback forms regarding this talk. And we can enter the paper presentation link, which will be given in the national webinar link, national webinar group, which we have already started. So thank you a lot, sir, for being with us and giving your expertise in the fuzzy field. Thank you, sir.